Hello, Math 1325 students. Let's begin Lesson 13, Techniques of Integration. Lesson 13 is a continuation from Lesson 11. Most of the time we'll study indefinite integrals, but do not completely disregard Lesson 12 because we'll study some definite integrals too. Let's begin with a review. Please remind yourself with some trivial rules. The standard rules, for power functions, in a special case when the power is -1, and exponential functions. And then some of the extended forms. The recurring theme here is 1 over a, again 1 over a, also 1 over a, and the reason is to undo the chain rule. If you take the derivative of the right-hand side, by the chain rule you have to multiply the derivative of the inside, and that's a. In order to undo that multiplication, you begin with 1 over a. But then again, in this case, the standard form will be a bit more useful for simplicity. In general, this is more useful because a special case when a is equal to 1, then we get the original form back. But for this lesson, the standard form is going to be more useful for the simplicity. Now, what do you do here? The majority of the topic here is the reversed chain rule, and the minority will be reversing the product rule, which we'll consider in section 3. So chain rule first. Here's a chain rule as we studied in lesson 4. Step 1, outside first, derivative of the outer function, and then step 2, inside stay the same, and step 3, multiply the derivative of the inside as color-coded, green, red, and blue respectively. Okay, and let's study how to reverse this step by step. But before doing that, let's have a bit of a character change. You see, in integration, we start from small f, which is the integrand, and we go to capital F, antiderivative function. And this is reversing, so let's begin with capital F, and then taking a derivative of that capital F. And then this capital F prime will be small f. Make sense here? Next, instead of g, let's take another character. Like this. Instead of g, let's take y and y prime of x. Let's do the same thing here. What did I do? Nothing much. Change your character small f to capital F. Change the character g to y, nothing more. And then one small observation. Capital F prime is small f. Does it help? Oh, yes, it does. Let's reverse it. Pay attention to this in particular. From here, okay, all right. Y prime, let's reverse it one more into, let's rewrite it once more into dy dx form. Will it help? I don't know. If you just prefer to keep it the y prime of x, that's fine. In any case, from here, take the antiderivative of both sides. Left-hand side is already the derivative, so taking antiderivative, you get just capital F back. Right-hand side, we're going to get an integral. Integral of this thing here. And what you end up with a composite function, inside is y, and times the derivative. So those two are the things you're looking for. Inside function, y, and then the derivative y prime. How do you apply those to these kind of example problems, or even worse, these kind of example problems? Let's begin. Ready? If you're not ready, stop the playback and take a deep breath and then restart. Okay, step 1, we want the inside function. Remember the reverse chain rule? Oops, not that. Inside function. That's my y of x. That's inside. And then take the derivative. No, nothing wrong here. Sorry about that. And then solve for dx. That's the standard process. What did I accomplish here? I'm looking for this. Inside is red, and I'm looking for the derivative part. Here, in this original problem, inside, all right, and dx. What is dx? That's the computation I did. How? By taking the derivative. Derivative dy dx, that's 2x, all right? And then most people will skip this, by the way, and go directly over to this derivative computation. That's traditional, and that's a little bit more convenient. This derivative computation, except that dx is on the other side, and that's all for dx. So that this is going to be y, substituted, y, and this is going to be substituted by this blue. And that's why this technique is called the integration by substitution. So, first substitution, this is y, and second substitution, this dx is 1 over 2x times dy. Now, do you see a simplification here? You should. Do you see this x and that x canceling each other out? Consequently, this is what we get. 1/2 x is gone, y to the 1/5 power. So what did I end up with? We started with something really complicated, but we got something pretty simple. We simplified this integral into something much easier. And this is an easy integral to calculate. I mean, just constant 1/2 times the antiderivative of a power function, add 1 to the power, 6/5, and then its reciprocal. That's the antiderivative, isn't it? Okay, all right. We have correct antiderivative. But is that the complete answer? Close but no cigar. Not quite yet. The reason is because, I mean, this is correct antiderivative. But as for the answer, this is written in terms of x. So you have to rewrite this in terms of x again. But y is 16 plus x squared, so we need another substitution. So therefore, this is equal to this thing here. Let me copy and paste the entire thing. But y is 16 plus x squared. And by the way, you can simplify this a little bit further. 5/12. And that completes the problem. So first substitution, inside. Second substitution, dx. And third substitution to get the final answer. That's why this is called the integration by substitution. Theoretically, it is reverse chain rule, but we use substitution. Let's do this one more time. Now I have another problem down here. And then we have to do this problem. And then here, please note that we have inside like this. And then dr to work out. So inside of the composite function, let's take another character. S is equal to r cubed over 9 minus 1. Okay, let's start from there. Let's start from there. And that will go right here. That's going to be substitution number 1. And then let's take the derivative. ds is 3 r squared dr, but with 9 before. So actually this is 1/3. That's the derivative computation, and minus 1 will be gone. And therefore dr is 3 over r squared ds. Ready to simplify this integral? So this is integral of r squared times u to the 12th power times 3 over r squared ds, excuse me. That's the quantity you're looking for. Red, and that's blue, so that you can see the substitution clearly. Okay? Inside, the derivative, so that dr, and then in integral, you're substituting inside and dr. So substitution number 1, substitution number 2. And then do you see a simplification? After all, the purpose of all this is to get simple integral. Indeed, you must have seen that r squared here and r squared down there are canceling each other out. So 3 u to the 12th power, what am I doing? S. ds. Sorry about that. I use character s, and okay, all right. Here we go. And the derivative is 3/13 s to the 13th power plus some constant c, and that completes the antidifferentiation. It's correct antiderivative. But this cannot be the final answer because the correct antiderivative it may be, it's written in terms of s. The original problem was written in terms of r, so let's rewrite this in terms of r, and that'll complete the problem. Therefore, this one is same as this, except that s is r cubed over 9 minus 1. And that'll complete the problem. What do you think? Please compare this problem with the previous problem and see if there is any kind of parallel. There should be. Inside, and derivative computation to get dx, derivative computation to get dr, substitutions 1 and 2, and get simple integrals to calculate, and substitution number 3 and number 3.